welcome to this problem walkthrough. In this session, we'll dive into problem number 234, Palindrome Linked List. This is a popular problem that tests your understanding of linked lists and algorithms for determining if a sequence is a palindrome. Let's explore the problem, analyze its challenges, and discuss approaches to solve it effectively. In this problem, you're given the head of a singly linked list, and your task is to determine whether the linked list is a palindrome. A linked list is considered a palindrome if the sequence of values in the list reads the same both forward and backward. For example, a list like 1-2-2-1 is a palindrome because the values are identical in both directions, whereas a list like 1-2 is not, as the order differs when read backward. Your input will be the head of the linked list, where each node contains an integer value. The output should be a Boolean, meaning you return true if the linked list is a palindrome, and false otherwise. To better understand this, let's look at some examples. In the first example, the input list is 1, 2, 2, 1. When you read the values forward, they form the sequence 1-2-2-1, and reading them backward gives the same sequence, so the output is true. Now consider the second example, where the input list is 1, 2. Forward, it reads as 1-2, but backward, it reads as 2-1. Since these sequences don't match, the output is false. Lastly, in the third example, the input is 1, a single-node linked list. A single-node list is always a palindrome because it reads the same forward and backward, so the output is true. Keep in mind the constraints. The list can have up to 100,000 nodes, and the values in each node are integers ranging from 0 to 9. Now let's consider some edge cases. First, if the linked list contains only one node, like 1, it is always a palindrome because there's no reversing involved, it's the same in both directions. For two nodes, if the values are identical, such as 2, 2, the list is a palindrome. But if the values differ, like 2, 3, it's not. Finally, for large inputs, where the number of nodes can go up to 100,000, the solution must be efficient. This means the algorithm should ideally have a time complexity of O(n) to handle such cases within reasonable time limits. Ensuring your solution is optimized for these scenarios will be key to solving this problem effectively. When considering approaches to solve the problem, one intuitive solution is to convert the linked list into an array and check if the array is a palindrome. This works because the sequence of values in a palindrome remains the same, even when reversed. To implement this, we traverse the linked list, store its values in an array, and then use two pointers or Python slicing feature to check if the array reads the same backward and forward. This approach is straightforward and has a time complexity of O(n), as we only traverse and process the list once. However, it requires O(n) additional space to store the array, which goes against the problem's goal of achieving an in-place solution. This limitation makes it less ideal for scenarios where space optimization is critical. A more efficient approach involves reversing the second half of the linked list in place and comparing it to the first half. The idea here is that we don't need extra space to check for a palindrome. First, we find the middle of the list using the slow and fast pointer technique. Then, we reverse the second half of the linked list starting from this midpoint. Once reversed, we compare the nodes of the first half with the nodes of the reversed second half to determine if the values match. To preserve the original structure of the list, we reverse the second half back to its original order after the comparison. This approach achieves a time complexity of O(n) for traversal, reversing, and comparison, while utilizing O(1) space since no additional data structures are used. The trade-off is that the linked list is temporarily modified during the process, but this can be mitigated as we restore it before returning the result. Another approach involves using recursion to traverse the linked list. The idea is to use the recursive call stack to reach the end of the list while simultaneously moving forward. By maintaining a pointer to the head node, we can compare values from both ends of the list as we return from the recursive calls. The steps involve recursively traversing to the last node, then comparing the value of each node on the way back with the current head pointer's value. After each comparison, the head pointer is moved forward to check the next pair. This method has a time complexity of O(n), as we traverse the list only once. However, it has a significant drawback: the recursive call stack requires O(n) space, which could lead to stack overflow for very large linked lists. This makes the recursive approach less suitable for scenarios with strict space constraints. The chosen strategy for this problem is the optimized approach that reverses the second half of the linked list. This method stands out because it provides O and time complexity while using only O1 space, aligning perfectly with the problem's constraints. The key insight is that we only need to compare the first half of the list with the reversed second half to determine if the linked list is a palindrome. Unlike the brute force approach, this method avoids using extra space for an array, and unlike the recursive approach, it doesn't rely on the call stack. The realization that we can manipulate the structure of the linked list temporarily, and still restore it afterward, is what makes this solution both efficient and elegant. While there is a trade-off in modifying the list during the process, this is an acceptable compromise because the list is restored before returning the result. This balance of efficiency, simplicity, and adherence to constraints makes the optimized approach the best choice for solving this problem. To solve the problem of determining whether a singly linked list is a palindrome, one straightforward approach is to leverage arrays. The key idea is to convert the linked list into an array, which allows us to easily perform a two-pointer comparison from both ends. First, we traverse the linked list node by node and copy each value into an array. For example, a linked list like 1-2-2-1 would result in the array 1, 2, 2, 1 after this step. Once we have the array, we use two pointers, one starting at the beginning and the other at the end of the array. We compare the values at these two pointers. If the values match, we move the left pointer forward and the right pointer backward, continuing this process until the pointers meet or cross. If at any point the values don't match, we know the linked list is not a palindrome. This method is simple and takes advantage of the array's random access capability to check for symmetry efficiently. The two-pointer comparison process stops when the left pointer meets or surpasses the right pointer, ensuring that all necessary elements have been checked. For the array 1, 2, 2, 1, the comparisons would look like this. First, compare the leftmost and rightmost values, 1 and 1. Since they match, move the pointers inward. Next, compare 2 and 2, which also match. At this point, the left pointer is greater than the right pointer, so the process stops. If all comparisons succeed, we return true, indicating the linked list is a palindrome. Otherwise, we return false. This approach relies on converting the linked list to an array because singly linked lists don't allow traversal in reverse, making it challenging to compare values from both ends directly. While this method simplifies the problem, it does introduce an O(n) space cost to store the array. This trade-off is worth considering, especially when working with memory-constrained environments. Lastly, edge cases such as an empty list, which is considered a valid palindrome, are also handled naturally by this approach. Other edge cases include single-node linked lists, which are always palindromes since there's only one value to compare. Additionally, this approach handles both odd and even-length linked lists seamlessly. For odd-length lists, the middle element is ignored during the comparison because the two pointers naturally skip it when they meet. The data structures used here include the array, which stores the linked list values to enable random access comparisons, and two pointers, which traverse the array from either end. The time complexity of this algorithm is O(n), where n is the number of nodes in the linked list. This includes the traversal to copy values into the array and the subsequent palindrome check. The space complexity is also O(n), due to the additional storage used for the array. While this approach is efficient in terms of runtime, its space usage can be a limitation. For improved space efficiency, we could explore an in-place solution that avoids converting the linked list to an array, such as reversing the second half of the list directly. By reversing the second half of the linked list and comparing it to the first half, we can achieve an optimized solution with O(1) space complexity. However, this approach is more complex to implement. Let's look at the code for the array-based approach. First, we define our listNode class and the isPalindrome function. In the function, we initialize an empty array to store the values of the linked list. Using a while loop, we traverse the linked list, appending each node's value to the array until we reach the end. Next, we use two pointers, left and right, initialized to the start and end of the array, respectively. In another while loop, we check whether the values at these pointers match. If they don't, we return false. If they do, we move the pointers inward and continue until they meet. Finally, if all comparisons are successful, we return true, indicating that the linked list is a palindrome. This code is straightforward and effectively implements the two-step process of copying values to an array and performing the palindrome check. To see this algorithm in action, let's walk through a couple of examples. For the input linked list 1-2-2-1, we first copy the values into the array 1, 2, 2, 1. Then, we compare the values at the two ends, 1 and 1 match, as do 2 and 2. Since all comparisons succeed, the output is true. For a different input, such as 1-2-3, we copy the values into the array 1, 2, 3. Comparing the values at the ends, 1 and 3 do not match, so we immediately return false. This example demonstrates how the algorithm efficiently identifies whether a linked list is a palindrome by leveraging the array-based approach and two-pointer comparison method. This implementation solves the problem of determining whether a singly linked list is a palindrome. The solution uses a straightforward approach by converting the linked list into an array, which simplifies checking for palindromic properties. Step-by-step explanation. 1. Copy the linked list to an array, the first while loop iterates through the linked list. Each node's value is appended to the values array. This step ensures that all the elements of the linked list are stored in an array for easy access and manipulation. By the end of this loop, we have a complete list of node values. 2. Two-pointer technique for palindrome check. Once the values are in an array, we use the two-pointer technique to determine if the array is a palindrome. The left pointer starts at the beginning of the array, and the right pointer starts at the end. In each iteration of the while loop, we compare the elements at the left and right pointers. If they differ, we immediately return false since the sequence cannot be a palindrome. If they match, we move the left pointer one step to the right and the right pointer one step to the left, narrowing the range. 3. Return true if palindrome. If the loop completes without finding a mismatch, it means the sequence in the array is a palindrome, so the function returns true. This approach is simple and easy to understand. The time complexity is O(n), where n is the number of nodes in the linked list, and the space complexity is also O(n), due to the additional array storage. This method is optimal for cases where the linked list size is manageable, and the extra space usage is not a concern. Here, we start by defining the structure of a singly linked list using a class called listNode. Each node in the list contains an integer value and a pointer to the next node. This structure will help us represent the linked list we'll be working with. Next, in the solution class, we are implementing the method isPalindrome, which determines whether a given linked list is a palindrome. The first step in this method is to copy all the values from the linked list into an array list. To do this, we initialize a new array list called values and use a while loop to traverse through the linked list. At each step, we add the current node's value to the array list and then move to the next node. This process continues until we reach the end of the linked list, resulting in an array list that contains all the node values in the order they appeared. Once we have all the node values stored in the array list, the next step is to use the two-pointer technique to check if the list is a palindrome. We initialize two pointers, left, starting at the beginning of the list, and right, starting at the end. While the left pointer is less than the right pointer, we compare the elements at these positions. If the values are not equal, we immediately return false, as this means the linked list is not a palindrome. If the values match, we increment the left pointer and decrement the right pointer to continue checking the next pair of values. This process continues until the pointers meet or cross each other, indicating that all pairs of values have been checked. If no mismatches are found, we return true, confirming that the linked list is indeed a palindrome. To determine if a linked list represents a palindrome, we begin by copying its values into an array. Starting with an empty list, we initialize values as an empty array and set current to the head of the linked list. As we traverse the list, we append each node's value to values. For example, with the input 1-2-2-1, we first append 1, resulting in values equals 1. Moving to the next node, we append 2, yielding values equals 1, 2. Continuing, the next value 2 is added, so values equals 1, 2, 2. Finally, appending the last value 1 gives us values equals 1, 2, 2, 1. Once we reach the end of the list and current becomes none, we proceed to check if the array is a palindrome. Using a two-pointer approach, we initialize left at the start of the array and right at the end. We compare values, left, and values, right. Here, 1 equals 1, so we move the pointers inward, setting left to 1 and right to 2. Next, values, left, and values, right, are both 2, so the pointers move again. At this point, left exceeds right, confirming that the array represents a palindrome. The function outputs true. Now, let's consider a linked list that does not form a palindrome. With the input 1-2-3, we again start by copying the values into an array. We initialize values as an empty list and traverse the linked list. First, we append 1, resulting in values equals 1. Next, we append 2, so values equals 1, 2. Finally, appending 3 gives us values equals 1, 2, 3. With the array prepared, we use the two-pointer technique to check for a palindrome. We set left to the start of the array and right to the end. Comparing values, left, and values, right, we find that 1 equals 3. This mismatch immediately tells us the array is not a palindrome, so we return false as the output. In the case of a single-element linked list, such as the input one, the process is straightforward. We first copy the linked list values into an array. Initializing values as an empty list, we traverse the linked list and append the single value 1, resulting in values equals 1. Next, we use the two-pointer technique to check for a palindrome. Here, both left and right are initialized to 0, pointing to the single index in the array. Since left is not less than right, the loop is skipped entirely. A single-element array is considered a palindrome by definition, so the function outputs true. To analyze the time complexity of our solution, we can break it down into two main steps. First, we copy the linked list values into an array. Here, the algorithm iterates through the linked list once, visiting each node exactly once to populate the values array. If the linked list contains n nodes, this step clearly takes n time. Next, we check if the array is a palindrome using the two-pointer approach. This involves comparing elements from both ends of the array, moving towards the center, and requires just one pass through the array, which again takes n time. When we combine these two steps, the overall time complexity becomes n plus n, which simplifies to n. This ensures the solution is linear in terms of how it scales with the size of the input. Now, considering space complexity, the primary contributor here is the values array where we store all the elements of the linked list. If the linked list has n nodes, the array will also have n elements, requiring n additional space. Beyond this, the algorithm uses a constant amount of extra space for pointer variables such as current, left, and right. These require 1 space. When we combine these factors, the overall space complexity is dominated by the values array, resulting in n plus 1, which simplifies to n. Importantly, the time complexity remains n in all scenarios, whether the input linked list is small, large, or contains special cases, since the algorithm must always traverse the entire list and perform the same steps for validation. Comparing this approach to a brute force or naive solution highlights its efficiency and simplicity. A naive approach might attempt to reverse the linked list directly and compare it to the original list, which would require additional space for the reversed copy and still take n time for traversal and comparison. In contrast, the current approach avoids modifying the linked list entirely. Instead, it uses an array to store the values, offering a much simpler and more straightforward method for checking palindromes. Finally, from a mathematical perspective, the traversal of the linked list to populate the values array is linear, as each node is visited once, contributing n time. The two-pointer comparison involves at most n/2 comparisons, which is also n. Summing these steps gives a total time complexity of n. The space complexity, dominated by the values array, remains n as well. This combination makes the solution both time efficient and memory efficient for solving the problem of determining if a linked list is a palindrome. When solving the palindrome linked list problem, there are several common mistakes to watch out for. First, modifying the linked list directly, such as reversing part of it in place, can lead to issues if the problem requires the list to remain unaltered. This is especially problematic in scenarios where follow-up operations depend on the original structure of the list. Next, ignoring edge cases like an empty list, a single node list, or lists with duplicate consecutive values can result in runtime errors or incorrect results. These scenarios require special handling to ensure your solution is robust. Lastly, not optimizing for space by always relying on auxiliary data structures, like converting the list into an array, can unnecessarily increase space complexity to O(n). Instead, consider using a two-pointer approach, which offers a more space-efficient O(1) solution. Another frequent mistake is inefficiently detecting the midpoint of the linked list. For example, counting all the nodes in one traversal and then iterating again to find the middle wastes time and increases the number of passes required. A more efficient approach is to use the slow and fast pointer technique to find the middle in a single traversal. Additionally, errors often occur during the two-pointer comparison phase. For odd-length lists, failing to account for the extra middle element can result in off-by-one errors and mismatches when comparing the first half with the reversed second half. Carefully handling these nuances ensures the correctness of your solution. From an interview perspective, it's important to clarify whether space optimization is required. Knowing whether O(1) space or O(n) space is acceptable can significantly influence your approach to the problem. A common pattern in palindrome-related problems involves two key steps: finding the middle of the structure and comparing the first half with the reversed second half. If you choose to use extra space, such as converting the list to an array, be sure to explain your reasoning clearly. For instance, you might justify that this approach simplifies the logic and reduces the chance of errors. Additionally, be ready for follow-up questions, such as optimizing your solution to use constant space or adapting it for a doubly linked list. Related problems, such as reorder list, middle of the linked list, and reverse linked list, often share similar techniques, so reviewing them can help you recognize patterns and refine your approach. There are also alternative approaches to solving the problem, each with its own trade-offs. The two-pointer and reversal approach is a popular choice. It uses the slow and fast pointer technique to find the middle, reverses the second half of the list, and then compares it with the first half. This method achieves O(n) time complexity while keeping space complexity to O(1). Another option is the recursive approach, which involves traversing to the end of the list and performing a backtracking comparison. While this approach is elegant, it increases space complexity to O(n) due to the recursion stack. Finally, you can use a hashing method, where you store the frequency of each node value in a hash map to check for a palindrome. While this method is less efficient in terms of time and space, it can be helpful for variations of the problem that involve rearranging the list. Each of these approaches has its strengths, and understanding their trade-offs can help you choose the best solution for a given scenario. That wraps up our discussion on problem number 234, palindrome linked list. We summarized the problem, explored a brute force solution, and discussed key takeaways like understanding palindromes and optimizing for space. Thank you for joining. If you found this helpful, be sure to like, share, and subscribe for more coding tutorials. See you in the next problem. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!